Good morning. So we will continue with our lecture around reverse osmosis today. And specifically, what I'll do today is, at least in the first part, I will cover the way in which membranes are made and what are the membranes that were well known for this process. Now, I talked to you about this pioneering work that was done by these two gentlemen, Loeb and Sourirajan in UCLA. This was the first time that a reverse osmosis membrane was made, which was suitable for actually conducting reverse osmosis. Just so that you know how it is made, I've taken this a part of a paper from published by the scientists from BRC who had made this. It is firstly a cellulose acetate membrane. So this is the cellulose structure, and what you're doing is that some of the OH groups, you are basically introducing an acetate group. So that's really what you're doing. And what happens is that in these membranes, as you know, there has to be some kind of a porosity for molecules to pass through. And in these particular membranes, what happens is that the porosity, there is a gradient. So there will be parts of it at one end which will be extremely porous. And as you move towards the other end of the membrane, it gets tighter and tighter. So much so that towards the end, you actually cannot see the pores, But on the other side, you can comfortably see the pores. So this is what it is, and the typical degree of functionalization is around 2. So you'll have, or maybe 2 per sugar, something of that kind. Although this again is proprietary and it can vary, and you can see the membrane preparation process where what you do is you first take the cellulose acetate in a solvent. For example, they took a solvent of formamide and acetone, and they've also spelled out what was the proportions, of the cellulose acetate and the solvents. And then what you do is that this was of course done in a impractical way. I mean, this is not how a commercial membrane is made, but they took a glass plate and then spread this solution on this plate, and then there is a means of removing all the excess liquid because you might have made the liquid layer too thick, so you can remove a part of it, and then you have the kind of thickness of this liquid which will enable you to get a good membrane. And then it says that the solution was cast on a plain glass plate inside a closed casting room where relative humidity and temperature were maintained at 55 degrees C and 25 degrees C. So these are very important process parameters for making this membrane. And then because they had put acetone, they allowed the acetone to evaporate, so they are letting it evaporate for about 20 seconds, okay? And at that point, what happens is that the resultant polymer with some solvent that you get, what you do is that it is immersed in an ice bath, and in the process, what happens is that this liquid layer of polymer forms like a gel, and so it was gelled. So then once it forms a gel, it's got a shape, and after that, they took it out, and then it was heated to different temperatures, and this is called annealing. So they're doing it at various temperatures from 72 to 80 degrees centigrade. And then after they've done that, then they are doing an evaluation to see whether it has the salt rejection property. So this particular membrane, let's say it was tested at about 40 bar pressure with about 5,000 ppm of NaCl solution. So it's not seawater. It was much less than seawater salinity. And from that, they would measure that what is the salt rejection efficiency, what was the flux, and you can see these are, see the water flux was measured. So all these measurements are done, and that's how you basically characterize the membrane.
So in the cellulose acetate membrane,
Yeah,
so I did not understand the part after acetone which was allowed to evaporate. Can
yeah,
you explain
one
that
second.
part again, sir?
I wanted to add to this question, sir. So,
Yeah,
why is formamide used as an additive in the solvent?
it's a good question. You can ask yourself, what is really forming pores? Why is it that pores are formed? After my acetone has evaporated, and I'm still left with the formamide because its boiling point is higher. But subsequently, what I'm doing is when I'm putting it, let's say suppose I put it into water, and I'm gelling it. Now, what then happens is that finally the formamide is getting dissolved and leaving the system, and wherever I had formamide, I actually end up getting a pore. Is it clear?
Yes, sir. Thank you, sir.
So what exactly do you mean by gelling?
A gel would not necessarily be a one-phase system. So there will be polymer which is swollen in that solvent. So it is like you can think of as a highly solvated polymer which can form a gel. So that it has lost all its movement, and that's what makes it so viscous. You understood?
Yes, sir. So last question, sir.
Yeah.
So in the cellulose acetate membrane, we were using water to for gelling.
In this particular case, they're not talking so explicitly about the introduction of water, but I think what they meant is were gelled in an ice cold bath. Means ice cold bath means it's an ice cold bath of water.
You will see a clearer description of this in this slide, which I have taken from another paper. What does it say? The resulting polymer films are directly immersed for 30 minutes in distilled water at 1 to 2 degrees centigrade. Water is effectively an anti-solvent. When one adds water into the system, effectively what happens is that the cellulose acetate's affinity for the solvent reduces. And in turn, the cellulose acetate molecules start interacting with each other. And that leads to a kind of a physical cross-linking. And because of that, you see there is an infinite buildup in the viscosity of the system. And that's really what causes gelation. Gelation is when something doesn't flow and its viscosity is very, very high. You can consider it as infinite.
Okay.
You understood?
Yes.
Huh? This is the technology that is used everywhere today to make RO membranes. No one really uses a cellulose acetate membrane, and I'll also tell you why. Now, what they did was they did it in a like a three layers. So the first layer was just non-woven fabric. So you take a very porous non-woven polyester fabric, and over the polyester fabric, what you do is that you make a polymer, and this polymer is typically a polysulfone polymer, very similar to the way what you saw that cellulose acetate was made. You dissolve it in a solvent like dimethyl formamide, and then this is passed through rollers, and the a thin layer of this polymer gets stuck on this fabric, and then finally after it comes out, it is gelled by passing it into water. What that does is that this polymer, which is soluble in DMF but doesn't have solubility in water, but DMF has solubility in water. So when I take this and then pass it through the water, water becomes like an anti-solvent, and it leads to the precipitation of this polymer. But the precipitation is not in the form of a powder. It is the precipitation in the form of a coherent membrane. And that was the unique part of this particular membrane polymer and the way this processing was done, that you got a continuous film. And this film has very high porosity. You can actually see the pores in an electron microscope. But this polysulfone is so porous that it doesn't reject the salts, but it will reject things like bacteria. So it's got a easily measurable porosity. You can see polysulfone layer, and the layer is you can see the fabric that you took is about 100 micron. You put a polymer layer which is about 40 to 60 micron. Now comes the trick. What you do is that over this polysulfone, you coat a layer of polyamide. This is done basically through the process of interfacial polymerization. So first, this particular monomer is soluble in water. So you can dissolve it, and you take your fabric with the coated polysulfone, you take it through this solution. So some amount of this diamine, metaphenylene diamine, sticks to this polysulfone. So it gets in. Then what you do is, since there is quite a bit of water which gets in, so you try to remove most of the water, maybe with the help of an infrared lamp, which is put online. And then what happens is that it is passed through a solution of an acid chloride in some non-polar solvent like decane or hexane. You take some solvent like that. So then the acid chloride will react with the amine, release HCl, and it will form in situ this polyamide layer. So this is your amide, C double bond O NH, and is basically a polymer of this. Now the reason why you take 3 functionalities and not 2 here is that if you took only 2, then I would only get a straight chain, but I need the polymer to grow in 3 dimensions. Otherwise, I cannot get a membrane. I'll only get linear chains of polymer. Okay? So by putting in the third one, effectively what you can do is that you can ensure that the polymerization happens in over a 2-dimensional surface. So you get a film of this polymer over the polysulfone. Now watch this. This polymer that is formed is extremely thin, maybe between 0.1 and 0.2 micron. So you can imagine this was 100 micron, this is about around 50 micron, and this is 0.1 or 0.2 micron. So what this polymer did is, it was remarkable that they were able to show that layer thickness is enough to reject the salts in your let's say seawater and allow only the pure water to pass through. But at the same time, because it was so thin, this particular layer, so the resistance to flow was kept to a minimum, and so you ended up getting a fairly good permeate flux because this layer was so thin. This particular polymer poses very little resistance at when you apply a pressure of something like 40-50 bar, because the holes are quite big. These pores are very big, so there's really very minimal resistance offered by these pores. But these things obviously will offer a very high resistance, because you can virtually not see the pores. So the water has to diffuse through this polymer, which creates a tremendous resistance. Okay? So that's the reason why you need to make this particular layer as thin as possible. And this is a work done by a scientist called Cadotte in the US. And he was originally working with Monsanto. I will send you his patent, Cadotte's patent, so that those who are interested can read it. It's an absolute landmark in the history of reverse osmosis, because all subsequent membranes were essentially they were made following Cadotte's process, maybe with some minor changes here and there, but that's about it. Now, if you were to quickly look at some of the advantages and disadvantages of the two membranes, why is it? Is it that cellulose acetate was all bad, and is it that thin film composite membranes are all good, or are there some things which are not so good about it? The advantages of the thin film composite membrane, one is that there is excellent hydrolytic resistance. The reason is because amides are much less vulnerable to hydrolysis as compared to esters. And a cellulose acetate is basically an ester. Esters are far more vulnerable, to hydrolysis. So the hydrolytic stability was much better, and this could withstand pH ranges of something like maybe 3 to 11. Whereas with the other one, you had a much narrower range of stability of the polymer. So you can imagine what a huge thing it was. There was a superior rejection of salts. The ability of the polyamide layer to reject salt was found to be much better. Many of the organics, which can also be present in some aqueous streams, were also rejected in this particular case, and that was also important because, like for example, today many of the waters have things like pesticides. There's a huge problem how to remove pesticides in water. These membranes do a reasonable job of removing the pesticides. Not a perfect job, but it's certainly much better than any other membrane. Okay? Now, you can see this is at the heart. It's got an excellent membrane flux, which obviously is important, and it says at lower pressures. Obviously, if I use lower pressures, then the work that I'm doing is less, and if I get a higher productivity because of the flux, then obviously my capital investment would go down because the same plant can give me more water. Now, this is again very important. When you are applying something like a 70 bar pressure on these membranes, you see, because of this pressure, there can be a compaction which takes place. Now, that compaction can actually close the pores, and your performance can deteriorate very rapidly, right? So, but what it was found is that this the polyamide layer is more resistant to this compaction effect. And then, as I told you, it's got a excellent operating pH range, and also fairly good temperature range. It can go up to something like 45 degrees centigrade. This is important because the reverse osmosis flux has been found to increase with temperature. Even though the osmotic pressure goes up with higher temperature, but the effect of temperature in terms of reducing frictional losses is less, so you sometimes may actually want to operate at a higher temperature. The disadvantage is, the biggest disadvantage of this membrane is that it has got low tolerance to chlorine. So inadvertently, suppose let's say your water is coming from the municipality and it has been chlorinated, or somebody has put bleaching powder in the water, and you are not aware of it, and you go and put your this water through the membrane, you could completely ruin the membrane. This has remained a problem, although to some extent the resistance has been improved to the chlorine resistance, but still, I mean, this is one of the biggest problems with this membrane. Now, the advantages of the cellulose acetate, one is that this membrane, and especially these monomers tend to be costlier, whereas cellulose acetate membrane is cheaper, and therefore the production cost is low. And because there is no aromatics in the cellulose acetate membrane, so that tolerance to chlorine, because the chlorine really attacks the aromatics, so the resistance to chlorine is better with the cellulose acetate membranes. The disadvantage is As I said, the biggest disadvantage was the much poorer hydrolytic stability, leading to a narrow pH range. The salt rejection wasn't as good, so that was another problem. The temperature range was also lower, 0 to 35 degrees centigrade. I mean, you have to be very careful because in our country, like in the summer, when your requirement of water is more, many water bodies, the temperature can go up to 40, 45 degrees centigrade. And then, of course, this membrane will get spoiled. Compaction issues are more serious in this particular membrane. And the permeability through the membrane was poorer, which means that the flux was less. And, I showed you the dramatic improvement that took place in terms of the energy requirement in reverse osmosis, which we went through. A lot of the credit for this must go to the changeover from cellulose acetate to polyamide membrane. But let me also tell you that never completely give up something, saying that people get so carried away, polyamide, that you forget that there are certain merits of the cellulose acetate membrane. Now, if you are a good scientist and a good researcher, many times what you do is you will say, let me find out what are the weaknesses, what was the problem, and that's the reason why I put this down, so that you can understand what were the problems. And then you can say, can I not try and overcome those problems? And maybe if you can, sometimes an old technology can be revived. It may not be so bad. Like, for example, this particular patent talks about something extremely interesting. What they found is that it wasn't the cellulose acetate as such, which was so serious a problem, but there were certain impurities which were present in the cellulose acetate membrane, and they were actually causing the larger deterioration in the performance of the membrane. So this particular patent teaches how to remove those impurities, and they're able to get a better result. And this patent is not so old. I think it was, yeah, you can see May 9, 2007, whereas the original membranes were invented in the late 50s. You can see that someone is working something like 45, 50 years later and trying to make an improvement. And the smartest people are those who sometimes can revive things which are which seemingly have a problem, and just make them better. So look at this. In fact, let me show you some photographs. So this is how the polysulfone is being cast. This polysulfone layer on the non-woven fabric. Now, most important is this room, where you are doing all this casting, etc. You have to have an excellent control over things like the humidity and temperature. In fact, it took us long time to figure out all these things. My colleagues who were working in the institute where I was the director, took years to actually do all this, and they were able to more or less make it perfect through a good understanding of the of things like the humidity and temperature. You may actually need to even put a dehumidifier if required, especially if your humidity level is too high. On the other hand, if it is too dry, then also is not good. You need the optimum level of humidity. Now, in fact, this I'm not sure whether it's still there, but this is a company in Pune who had licensed all this technology, and they had gone into production in Pune. This is the first RO membrane manufactured in our country, the thin film composite membrane production. And just so that you can see, first, of course, you are taking the membrane with the polysulfone layer. So this is how it was put. Okay, so you're taking it in, and then you are passing it through the metaphenylene diamine solution. Okay, so the amine is going in, and then it is going into your solution of acid chloride, the trimethyl chloride, this solution, and then the polymerization is taking place. And then at that point your polymer is still not a very strong polymer. And so what you have to do is that you have to cure it at a certain temperature. But even after curing, what happens is that there will be some residual monomers. There might be unreacted metaphenylenediamine. There might be some trimethyl chloride which has got hydrolyzed. Didn't really form the polymer, so you may need to remove it. There could be other, like some of the solvent which might be stuck there. So you need to do a post-treatment to remove all of those things. So, you can see this is the post-treatment zone. So this is where you will try to remove all the impurities. And then you finally, because there are certain solvents which are used in this process, then, you have to basically dry it and then of course roll it. And that's your membrane. Now, what is very, very important, there are only a few organizations in the world which really had developed the capability of making these membranes. And some of the very critical things, like for example, over here, when you are taking the polysulfone DMF, and then finally you're putting it into water, and then you are getting your polymer. Now, there can always be certain trace amounts of the solvent, the DMF, which can remain along with your membrane. And that can very severely affect your subsequent performance during formation of the polyamide layer. So what you need to do is that you need to have, and I'm talking about concentrations in the range of ppm. I'm not talking about things which are present in percentage concentrations. So what kind of a technique will enable you in a continuous process to actually detect that whether you have got too much DMF and it's off spec, in which case you'll need to wash it better. So for example, after a lot of painstaking effort, it was found that the refractive index changes, which take place in the water because of the presence of small amounts of solvents like DMF, can actually be measured to the 4th decimal place through special instruments. So that can be used as an online technique to tell you whether you're doing things right. So I hope you can understand the sensitivity. Now, look at also how critical things are, and this is really where industrial engineering comes in. I mean, I can make anything. The question is, can I make it well? Can I make it such that it is commercially useful? Like, for example, I told you that you have to keep this polyamide layer such that it is very thin, and that will help you to maximize the flux. But at the same time, there cannot be any defect in this polymer. And when you're trying to make something very thin, like let's say less than 0.1 micron or thereabouts, you're talking about nanometer size. Even a dust particle can create a hole. It can create a defect. And you might find your whole membrane is spoiled. So that's the criticality, which doesn't show up many times when you're doing something in the laboratory or you're doing it for a publication. But when you're developing technology, it's absolutely vitally important. Let me just show you, for example, the painstaking effort that was taken to optimize the thickness of this polyamide layer. So, and at that stage, it was being actually looked at for brackish water desalination with maybe about 5 to 10,000 ppm salinity, maybe 1/3 to 1/5 of seawater salinity, thereabouts, or 1/8 of seawater salinity, something of that sort. Now, what was found is that if you measure the water flux, the permeate flux, which is vital for productivity, and you look at in the x-axis the polyamide film thickness. Now, this itself, sometimes you have to develop technologies for analysis. After a lot of effort, this technique was developed. This is actually an infrared technology based on what is known as grazing angle, infrared spectroscopy. Don't worry about that. but effectively what that does is that you can measure the thickness of your polyamide layer by monitoring the amide peaks in the infrared, and simultaneously you measure the flux. Now what was found is that, and you can see the thickness varied from something like 0.12 micron to about 0.25 micron, so within that range. And what you found is that like if I make it thicker, okay, it had a salt rejection of around 96%, which was quite okay for the kind of level of sophistication that was used in all this equipment. But the flux was very poor, so it was barely 10 gallons per square feet per day. Now, when that polyamide was made thinner, say you came to something like 0.20 or 0.18 micron, not a whole lot of difference. And your salt rejection efficiency did not really change so substantially. But look what happened to the flux. It went up by almost 3 times. So this membrane was 3 times more productive than this particular membrane with 0.24 micron thickness. Now, if you try to get more greedy and go further, okay, and making it even thinner, like it has been done, say going up to say something like 0.16 micron or thereabouts. What happened was that, of course, there was a further improvement in the flux, but now you can see there was a sharp decline in the salt rejection efficiency. So what it means is that you have gone too far over here, and here you've unnecessarily made the membranes less productive. So obviously the most ideal would be a region somewhere here. Also, there will be a continuous method of improving the analysis. So, for example, when this work was done around, I think around 2002 or 3, when this technology was first developed, at that time, this infrared grazing angle technique was used. But subsequently, it was possible to develop a very nice electron microscopic technique. So this is your polysulfone layer. You can see it's much more spongy and got a lot of pores. And this that you see over here is your polyamide, where you will virtually not be able to see any porosity. It's a dense polymer, and that's what is giving you the salt rejection efficiency. Is that all clear? Did you understand?
Yes, sir.
Okay. And then, of course, once you have made the membrane, you have to cut it to the right size. Then I'll show you why you need to do this. This is how the membrane modules look. You remember yesterday I showed you a picture of thousands of these membrane modules in a plant. What happens is it's a very, very sophisticated design. So many of you, suppose later on, some of you get interested in the area of fluid mechanics. You might want to study this particular configuration of the membrane. What it does is that you have got your membrane, and between two membranes, okay, you have to put a spacer, and likewise on the back side of the membrane also you have to put a spacer. One is called the feed water spacer, the other is called the product water spacer or the permeate water spacer. So this is the spacer, and this is also what is important to prevent the compaction, because you need a pathway for the water to flow. So you have to create some space for the water to flow. That's what the spacers do. And this configuration is very interesting. It's called the spiral bound configuration. At one end, all these, there will be about, say, maybe 30-40 leaves of this membrane, and all of them need to be sandwiched and they have to be welded on one side, and the other side is open. Effectively, what it does is that the feed water is flowing from here. It is passing through your membrane, and the feed water from each of these sheets is all collecting in a central tube. And so this is your permeate. So your permeate is coming out from here, and the reject water is coming out from another port, the concentrate, and this is your entry of the feed water. Okay, so effectively this whole thing is really to produce this kind of a membrane with module with many of these sheets. That's what is being done. Finally, you have to also give a fiber reinforced plastic coating because just so that these modules can withstand some pressure, and they can also avoid some accidental dropping and things like that, which can cause some problems. And then finally, these are put inside a pressure vessel, and that pressure vessel has to be able to withstand the kind of pressures that you want to use. So if you're trying to do seawater desalination, obviously you'll use a pressure of something like 70 bar, and so your pressure vessel must be able to withstand that. So this is your pressure vessel, this one, okay, and inside that is your these membrane modules. And finally, then after that you test it out, and once you're absolutely certain that it conforms to all the minimum specifications which you have indicated, then you can pack it, and it can be exported or used within the country. So with that, I come to the end of desalination, and now what I will do is the rest of the time I will introduce you. Today we will talk first about raw water, and then in the next class I will, and probably I'll try to introduce wastewater, and in the next class we will really spend time talking about how wastewater is managed, because that is such an important area, management of wastewater. But before I come to wastewater, let me tell you what happens when an industry takes in raw water. Now, it all depends on what is your source of raw water. Today, as I told you, many industries, their source would be desalinated seawater, or it could be coming from the municipalities, or there might be a river flowing next to your factory. You might draw the water from the river. Many times, your water will have turbidity. Your water may have hardness, which is deleterious for your process. So what you have to do is that you may want to give it a treatment with lime and soda to remove hardness, maybe magnesium as magnesium hydroxide and calcium as calcium carbonate through this combination. And then whatever are the very fine particulates which are present in your water, you may add alum to settle those so that you get a very clear water. So your raw water is going from here, and then you are passing it through these, that's where it's coming from, and then finally you're getting your water, which is clearer. So it's going from here and it's coming out. Then what you may also want to do is, because you have added some alkali, okay, you may have to do a pH adjustment with carbon dioxide. So you may require some recarbonation. And then your water might have some organic. So you may have to treat it with something like activated carbon to basically get rid of those. And then after that, obviously, there could be some particulates, which again, you might use a sand filter, clarify. And if you're suspecting some bacteria and things like that, which might be present, and there could be a problem, then you might want to chlorinate, just so that, you don't have any growth of bacteria. By the way, I must come back to this, and I find that all of them have glossed over one very, very important issue, and I'll put it down and I'll call it membrane fouling. This is the biggest problem in membrane technology. Membrane technology otherwise is many times quite good. This is a huge problem, is still a huge problem. And you can see that all of them have conveniently left it out. But most of the time, you have to chuck away a membrane after some time because it has got foul. So keep this in mind. And I'll put again, not an issue to remain silent about. This you have to confront hands-on. So if you want to know what is a really great area to work on, I will say try to make anti-fouling membrane. It's a very, very important area of research. So after that, you have got your water, and these are, by the way, the typical precipitation processes that occur when you add lime and soda and things like that. This school chemistry, so you'll have no problem understanding it. Let me now tell you what happens, and we have seen that when we introduced initially this area of water, and we said that it goes into an industrial process. Some of the water may get incorporated in your products. Some of it may become a waste stream, and so it has to be discarded. But it could be that through some adjustments of your wastewater, you might be able to recycle a part of it, if not the whole of it. So, for example, this gives you a problem. Like, let's say you've got an industry, and in the industry you're carrying out a factory, you're carrying out some processes, So this is your inlet water, this is your outlet, and after that you do some treatment also of the water, but the water, even after the treatment, is not suitable for recycle. So, for example, let's say there is a limit on the amount of chloride which can be present in your water, and say I have put in water, with a certain level of chloride, and the operations which are involved in my factory, let's say they introduce chloride, maybe sodium chloride, I have to add it for something or the other. And so what can happen is that at the end, I may have too much chloride in my water, and even after the treatment, I can't put it back, because of the high level of chloride. Now, at that point, the smart thing to do is not to chuck away the whole thing. I might say, oh, let me find out how much chloride is actually present over here after my treatment, and what is the acceptable level of chloride in my process. So I can say, all right, so let me throw away part of that wastewater which I've created. So that would be a discharge, and the process of throwing it away is typically referred to as blowdown. So I'm getting rid of it. And in turn, what I'm doing is I'm topping up with fresh makeup water to compensate for the amount of water that I discharge. So I discharge water with a higher amount of chloride, and I'm making up with the water with lower amount of chloride, so that my overall chloride levels are acceptable. So let me quickly run you through this problem for a blowdown rate of 10%, which means that if I, let's say, I had 100% water, I'm allowing 10% to be discharged, and they're giving you, for a blowdown rate of 10%, calculate the equilibrium concentration of chloride ion in the water in the recycle loop, given the following information. And it may be a continuous process. So continuously, I'm doing this, and every now and then I'm discharging 10%. So what they're saying is that let the total volume of water in the entire factory recycle loop be 1 million gallons. They have shown it in gallons, but I can express it in liters also. So 3.78 liters. So that's what I have got. And now what they're saying is that in the makeup water which is added to the factory, from municipality or whatever, the raw water, the makeup water, which is the raw water, let's say it has got 10 milligram per liter of chloride. And in your factory, say you're carrying out some operations, and which is contributing about 90.5 pounds per day. So I can convert it into kilogram from this. Okay. So and I know how much of this is gone, and I also know how much came from my makeup water, how much chloride came, and they had done a treatment here. What they're saying is, in this treatment process, no chloride was removed. So this treatment removed other things, not the chloride. And the blowdown was 10% over here. That's what they've said. And what they're saying also is that, not only the amount that I'm blowing down, but in my factory, because it's quite hot, there will always be some evaporation losses. And so what they're saying is typically the evaporation loss is something like 5% of the total amount. So if I've taken 1 million gallons, so I'll have 5% means 50,000 gallons per day is my evaporation loss. So my makeup will be both the amount that I blew down over here plus the amount that evaporated. So that is my total intake of water. So what you then do is you do a standard mass balance. That's what I've written over here, that 0.1 million gallons through blowdown plus 0.05 million gallons which evaporate, so 0.15 million gallons. And the incoming water has 10 ppm, 10 milligram per liter is the amount of chloride in that water. So you can convert the gallons into liters over here. If you want to estimate it in pounds, then you convert kg into pound, and then we know that 10 ppm means 10 into 10 to the power minus 6 kilogram per liter is what you will have. Okay, so if you multiply this whole thing, you'll get 12.5 pounds of chloride, which is coming from the water you are taking into your factory every day. And then in the factory, what it says is that, because of the operations, there is another 90.5 pounds being added. So this is the total amount, 90.5 plus 12.5 pounds, which is equal to 103 pounds, which is what is being added. Now, if you want a steady state operation, then in that 10% of the wastewater which I'm discharging, it must contain 103 pounds of chloride, because then the amount that I'm putting in is compensated by the amount that is being discarded as blowdown. So, but I don't know what is the concentration in the recycle loop. That is what I have to estimate. So, suppose its concentration is y ppm, y milligram per liter, then basically whatever is there in my recycle loop, the same is what I'm blowing down. It's not a different water, it's the same water which I'm blowing down. So effectively then what I'll have is that the total amount of chloride in my blowdown will be equal to 0.1 into 10 to the power 6 gallon, because 1 million is what is there in my loop and 10% of that. And then gallons is converted into liters, 3.785 liter per gallon, multiplied by y milligram per liter and expressed in kilogram, 10 to the power minus 6 kg per milligram, and multiplied by 2.204, which is pounds per kilogram. And so this, if you multiply, you'll find 0.834 y. So 0.834 y pound must be equal to 103 pounds, because that is the amount of chloride that I have to let go so that it doesn't accumulate in my plant. And so from here, if you do the calculation, y will be equal to 123 milligram per liter. I've taken y as milligram per liter, so that's the same. So this is how one can conserve water, by blowing down a part of the water and then only taking in that amount which I require. All of you followed the lecture?
Yes, sir.
Okay.